Hi, y'all. Welcome back to another round of physics, and we'll keep going with this energy bit today. So the first thing that I would like to sit and talk about, let's get this back up and running here. First thing that I would like to talk about today is thinking a little bit more about this choice of system and surroundings. So as emphasized, or as I keep trying to emphasize to you, that it's really important that we sit down and we think about what our system and our surroundings are prior to starting a problem. And in fact, I mentioned this a lot with the forces. This is generally where it really becomes important for the first time. And then I will also call to your attention that previously I was really specific or really adamant that you also talk about your initial and final states. And this, of course, was when we were primarily dealing with kinematics that becomes particularly important. Now, if I actually go and look at the definition of work, so I'll go ahead and write it down right here. You have work is defined as being F dot dr. Or if you'd prefer, if you'd like, actually maybe I'll do it this way. If you prefer for a moment, if you'll allow me, I'll write this as a delta r. And hopefully now you see why I was so adamant that you start practicing the system and surroundings when talking about forces. And the initial and final state, especially when you're talking about kinematics, in other words, displacements. Because here, when I actually look at the definition of work, I now have forces, so I should be doing system and surroundings. But I also have delta r's, displacements, and so I should be thinking about initial and final states. So when you're doing an energy problem, you really, really need to start doing all four of these now. It's not just system and surroundings and you're done, or initial and final states and you're done. You have to do all four of those, and that just comes down to helping set up the equation properly. Okay? Now, this whole point, why did I start out the video like that? Hopefully you'll see in a moment why, but I would like to start introducing some other types of forces. So last time we started with Newton's second law, F equals ma. And we went through and basically showed the work kinetic energy theorem. We said we do some little derivations, and eventually I show you that the work is equal to the change in kinetic energy of the point particle. And then I went and said, wait a minute, this is for a point particle. I'll just abbreviate that as PP, point particle. And said this point particle is located at the center of mass of the system. Okay. So if we conceptualize our entire system as just a single point located at the center of mass, then this is all we need. The work kinetic energy theorem will give us the relationship between the change in kinetic energy of the point particle, or of the center of mass if you prefer, and its relationship to the work done by the surroundings. But what happens if you don't want to do that? What happens if you have what I call a multi-particle system and you don't want to consider it as a single particle? So I'll say multi-particle system. Then what do we do? And I'll just run through some examples here. I just want to run through a couple of them. And first of all, thinking about our rules of energy, we'll figure out that if we want to consider multi-particle systems, we're going to have to introduce some new forms of energy. So, first off, why don't I go ahead and play this video for you? Take a minute, play the video. I'll be right back. Okay, now we're back. Sweet. Let's get an idea about this video. So the first thing is let's go ahead and for a moment, let's consider just the system as the cart. System as the cart. meaning the surroundings. We have things like the band, the surface, I'll say earth, excuse me, I started writing an E there, so earth and the surface. So the rubber band provides some force, I'll just call that one F. This one is Fg, and that would actually be into the screen. And the surface is our normal force coming out of the screen. Okay. So here, it's pretty easy. We notice that, okay, well, if from the overhead view, as our cart initially hits our rubber band, so I'm just drawing the physical diagram right now, as the cart actually hits the rubber band, right now it has a non-zero kinetic energy, put greater than 0. Then in the process, during the collision, the band starts stretching. I'll just draw a stretching band here as the cart hits it. And the force of the rubber band on the cart is this way, right? F. And the displacement of the cart is this way. And we notice right away that when these two are anti-parallel, this means that the work will be less than 0. Okay? Now, because the work is less than 0, and I just have my cart, I'll consider my cart as being a point particle, that means that the change in kinetic energy of the cart is less than 0. In other words, I'll say V final is less than V initial. Now, I don't think this is any surprise, and hopefully that makes sense to you. Okay. Now, here's the next question, though. What happens if instead of just the cart, I decide to put the cart and the rubber band into my system? I still have the surroundings. You could say something like the earth and the surface. Sorry, that's a bad U. You could say the earth and the surface. But when I actually start looking at the situation now, say initial before impact. And why don't we go ahead and say, let's take a look and say our final is cart stopped. Okay. Now, if I'm thinking about these initial and final state here, let me ask a couple questions. So for example, initially, what can you tell me about the initial kinetic energy? It's greater than 0. How about the final kinetic energy? Keeping in mind what I've chosen as my final state. It's exactly 0, right? There's a moment with the cart has stopped, nothing's moving, and so the kinetic energy is 0. And so here's the trick, is that if I then apply it into my work kinetic energy theorem, so I say, okay, well, if this is true, and my work kinetic energy theorem is true, kinetic energy, this side of the equation, right here, is less than 1. Final is 0, initial is greater than 0, final minus initial will give me a negative value. So my delta KE is less than 0. Now let's take a look at the work. And from, let's see, I'll call this the side view. Side view. So it's as if we took our eye and put it level right on the table. Okay. And you have, let's say, here's your cart. You have the normal force acting up on the cart. You have the gravitational force moving down on the cart, or working downwards on the cart. And I should ask, with respect to the normal force or the gravitational force, what direction is the displacement of the cart? It's perpendicular. Okay. Now, I'll say that the displacement of the cart was this way. Okay. So notice I'm not doing a free body diagram right now, but I'm just drawing my physical diagram. And so if my displacement is perpendicular to the force, what's the work done by either of those forces on my cart? 0. Okay. We can see that. Let's go back. Work is the dot product of my force with the displacement. Okay. I could rewrite this if I want using these definitions that we talked about in the first chapter. Namely, I'll use the cosine of the angle between the two. And right here we see cosine of 90 degrees is 0. Go ahead and put that in there for you. That means that neither the Earth or the surface, I guess neither the Earth nor the surface do work on my system. That means looking at this, the total work should be 0. So my total work is 0, but my kinetic energy is less than 0. It looks like this equation is not correct, right? The work is 0, the kinetic energy is less than 0. It looks like this equation is bogus. And indeed, you could argue that this equation is bogus. It's bogus because we have two objects, and implicitly we're actually thinking about them as two separate objects. What do I mean by that? Well, for example, if we wanted to actually consider it as a single object, the cart, and I'm going to the overhead view here. If we wanted to think about the cart and the rubber band, if we wanted to model it as a single point mass, okay, where should we locate it? Your gut might tell you, oh, I should put the point mass here, right in the center of the cart. But that's not the only object. You also have the rubber band. The rubber band has a little bit of mass. And so it's not fair to put it right here. You'd actually have to figure out, and we'd have to measure the mass of the rubber band and its distribution, but we'd probably be actually slightly further forward in the cart, something like right here. Okay. The other trick would be, is that what can you tell me about the velocity? I'll say, what can you tell me about the velocity of the center of mass as compared to the velocity of the cart? Got it? Well, the velocity of the center of mass depends not only on the cart, but also the rubber band. And if you will, it's almost like an average. We'll go into that later, save it for rotational motion. What I will say here is that because the rubber band's not moving, or because the rubber band is stationary and the cart is moving, the velocity of the center of mass is going to be less than that of the cart. Okay. So if you actually want to use this idea, this rigmarole here, we're going to actually have to consider this whole thing and look at the movement of the red X. There's a bunch of other stuff to get at. I don't want to go into too much detail about it. There's got to be an easier way. And indeed there is. We're going to keep the two objects in our system separate in our mind conceptually. Okay? And what we're going to do is rather than thinking about the center of mass, what we need to do is introduce another form of energy. So the form of energy that we're going to introduce is called, in this case, it's called potential energy. And the reason that we use the word potential, or why we call it potential energy, what distinguishes potential energy is that it's stored energy, and I'll put even more on it, can be given back. What I mean by that is it briefly gets potential energy is, under certain situations, can be given back. It can be reconverted, if you will, back into kinetic energy. Okay. So now I'll leave it like that, but you'll see we'll actually have several different forms of potential energy in this class, and you'll run into a couple of others that might go beyond the scope of this class. Okay. But the idea is it's stored energy that can be given back, okay, reconverted back into something else. So in this case, where we're dealing with the cart and the rubber band, there's a form of potential energy that gets stored. And you could probably you already probably know what it is. We'll call it the spring potential energy. Spring potential energy. And ask yourself for a moment, what do you think the observable would be for the spring potential energy? It's how much an object is deformed. This is the energy that we will associate when an object in our system becomes deformed. It deforms, it doesn't do that for free. Okay. So the observable here, say the observable is a change in shape. Change in shape. Okay. Excuse me, that's really ugly. Let's try that again. The observable is a change in shape. So this could be stretching, it could be smashing together, it could be flexing like a trampoline surface or a rubber band. Okay. Now, let's see here. We can go a little bit further. So, So how do we get an expression for the spring potential energy for this situation? And some of it goes back to considering the rubber band in the surroundings. So let's go ahead and clear the table, and let's think about that for a second. So if I were to put it in the surroundings, so going back and thinking about the initial case where the rubber band's in the surroundings. So I have the system of the cart, and I'll put the band in the surroundings, along with the earth and the surface. But right now, the important piece is we need the band and the surroundings. And if I wanted to calculate, for this situation, if I wanted to calculate the work done by the band on the cart, we have an expression for that. And here we're going to have to use the most formal definition. We have to use the integral of the force dotted into the displacement dr. Now, if you recall, this is a mean force. That's why we have to put the integral in here. Okay. And this mean force is the spring force. Say F equals Kx. There's a negative in there. Say X hat. Okay. So what we'll do is let's go ahead. We have the overhead view. Here's our system and our surroundings, cart and the rubber band. And what I'll do is I'll call this direction the positive x direction. Okay. So this x represents how much the rubber band is being stretched by as the cart hits it. Well, in this case, let's go ahead and substitute in some stuff. The force acting on the cart will be in the negative x direction. Okay. The displacement will be in the positive x direction. So let's go ahead and put all of that in. So I have the force is in the negative x direction. So I'll take a magnitude, k times the stretch length, and I'll remind myself it's in the negative x direction. The displacement, I'll dot this into the displacement, which is in the positive x direction. So I'll write that as dx, infinitesimal displacement in the x direction, and then we'll have to take an integral. Now we see I've got an x hat dotted into an x hat. So 1 times 1 That'll give me 1. And I have a negative k integral of x dx. Now here's the question. Say, even if we haven't seen integrals before, we've seen some derivatives. So here's a different question I want to ask you. Okay? The derivative of what function, f of x, will give me x? So again, I'll ask you, the derivative of what function, f of x, will give me an answer of x? So go ahead, pause the video, hack that out. Okay, good. Hopefully you see that, okay, well, I know power rule. Okay, so I know that, okay, I've got power 1 here. Okay, so maybe, hopefully you start guessing checking something like x squared. If I take a derivative of x squared and apply the power rule, that gives me 2x, which is awfully darn close to what I'm looking for. The only thing I need to add in here is if I put a 1/2 on both sides, then I get, okay, well, d dx of x squared over 2, that is equal to x, which is what I wanted to find. Okay. Now, how does this work? This notation, this integral notation, does exactly what you just did over here. Okay. This integral notation is saying what function, if I take a derivative of it, will give me x. Okay. So right here, I'll put negative k, and I'll put x squared over 2. Okay. So evidently, the work done by the band on the cart is written as this expression. Okay. And I'll remind you again, k is how stiff the rubber band is. It's called the spring constant. X will be how far you stretch the spring, or the rubber band in this case. And you notice that this 2 just comes in. Good so far? So now let's go ahead, and I'm going to save this answer. We'll put it right up here. Okay, good. So let's go ahead and get rid of this, because now we're going to use that answer to ask ourselves, well, how do we fix our problem? So now, if we go ahead and we put our system as the cart and the band, and again, as our surroundings, we have the earth and the surface, but they don't do any work. Okay, so I'll put earth and surface here. I guess I'll put band, earth, and surface. They were there for our first problem. So here's the issue now. As we previously discussed, we had something. We applied the work kinetic energy theorem, and we had 0 here, and we had a value less than 0. Just put it like this. Okay. And now the issue is that we haven't accounted for all of the energy. The rubber band, which is now in our system, stores the energy. So we're gonna introduce a new term called the potential energy, U. I'll call it U spring. So we can't apply the point particle situation anymore. That's a no-no. What I do like, and this is why I introduced it, let's just apply a more general equation. Work is equal to the change in energy of the system. You'll notice that this is very close to the first law of thermodynamics, which I mentioned in a previous video. Okay. And if we do this, then we're good, because since we now have included the band in my system, we have a second form of energy that we need to account for. Namely, we have our change in kinetic energy plus the change in the potential energy. And that entire thing should be equal to the work of the system. Now we see, okay, well, W, this is equal to 0. This must equal the change in kinetic energy plus the change in potential energy. There we go. And all I'm going to do is move this to the other side. Oops, excuse me. Sorry, I thought I had that deactivated. So I have our change in kinetic energy is equal to a negative change in potential energy. And don't forget, this is the change in the kinetic energy of the cart. Good? So now the kicker. Looking at the first time when the cart was the system and the band was in the surroundings, I had an expression for the work that evidently was the change in kinetic energy of the cart. I have a second expression considering a different system, which also gives me the change in kinetic energy of the cart. These two, what I have boxed up here and what I will quickly have boxed down here, those two evidently must equal each other, right? They both describe the same thing, the change in kinetic energy of the cart. These two must equal each other. So let's go ahead and put those two together. If I eliminate the change in kinetic energy, I get something that says the work done on the cart must be equal to the negative change in potential energy. Right? If I set work equals kinetic energy, which equals the negative potential energy by the, transitive property, that must mean that the work is equal to the negative change in potential energy. Which means a change in potential energy for this situation is just 1/2 kx squared. The energy stored in the rubber band during this situation must be given by that. Now take a minute, think about just what happened there. If I put the cart into the system, and it's only the system, then the work done on the cart by surroundings is given by this boxed equation up here, highlighted. If I include the cart and the rubber band in the system, I no longer have work being done on my system. But I have an additional form of energy associated with the stretching of the rubber band that I must now account for. Okay? That's what this is saying. And by setting those two equal to each other, I can get an idea about the equation, the quantitative expression for the change in potential energy. That's given down here at the bottom. So you notice if you put the rubber band in the surroundings, then you're talking about net work done on the system. If you put the rubber band into the system, then you just have two different types of energy to worry about, and you don't have to worry about work at all. And it's not by accident that essentially the work and the expression for the change in potential energy are exactly the same, differing only by a sign, a negative sign. And the reason for that is you have to move, if you're thinking about the work, the first law of thermodynamics, delta E of the system, to move work from one side of the equation to the other side would require you to add a negative sign in. Right? By moving the band into the system, what you're essentially doing is taking a piece of this work and you're moving it and now considering it to be part of the energy of the system. So, what I want to remind you of is, again, we were talking about the cart as being the system. So let's go ahead and think about this as a different way. You say the system is the cart. It's the cart. And the surroundings are the rubber band. Okay, band. And under this choice of system and surroundings, we can kind of think about the situation as this. There's two different accounts that we have to deal with. We have the cart, which is our system, and we have the rubber band in our surroundings. And as we move from the initial state to the final state, what's going on is that the cart continually transfers energy from, the cart is continually transferring energy from its bank account, if you will, to the surroundings. So say it begins contact, okay, it's transferring some money, and then later on it transfers a little bit more, and later on it transfers a little bit more. So as this collision process goes on, it continually transfers more and more money from its own bank account, the system, into the surroundings during that collision process. Now, of course, the latter half of the collision process, say if you chose a different set of initial and final states, the band actually transfers it back. Okay. Now, the next question comes into play is, okay, well, again, we've got that. What happens if the band is actually in, just keep getting the wrong layer, sorry. What happens if the band is actually in our system? Okay. So in other words, we're taking the band and we're moving it into our system. Just move it right over. So we'll move that right over here, band cart system. So no longer is energy or money being moved from the system to the surroundings. Right? Or I talked about there's no work being done by the system or the surroundings for the cart and the band in the system. So it's not like money's moving over into the surroundings anymore. No, that's not happening. But something is going on still. So how I think about this in this situation is all of the energy stays inside the system. The question is, what form is that energy actually in? So starting out with, all of the energy is kinetic. And so what I think of is that everything is in the kinetic. This is all kinetic energy. As time progresses, as we move from the initial state to the final state, more and more of this energy becomes potential energy. Right? It all starts out as kinetic energy. I'll put KE here, KE, if you can read that, and kinetic energy, KE. But as time progresses, it no longer is kinetic energy. It gets transferred into a potential energy. It's transferred into potential energy. And then later on, of course, well, that's when it hits the final state, when it's fully stopped. All of the energy is now potential energy rather than kinetic. It's kind of like how a bank account, for example, if you're thinking about money again and you were actually thinking about your bank account, you could say, well, in my bank account, there's two separate pieces. And this isn't too much. You could think of one as being savings. You could think of one as being like your checking. And if you have a set amount of money, right, you have some money in your checking, it doesn't hurt to move it into the savings account, right? You don't lose money by moving some from your checking into your savings. You can move some over into your savings without losing any money. Now, where it's at, what form is it? That's slightly different, right? You have two accounts, so one's, you haven't lost total amount of money. It's just where is the money located. Same idea over here when we're talking about the band cart system. It's not that you're losing money into the surroundings. That's not what's going on here. Okay? Rather, you're simply changing where the money's located. You're putting it into potential energy instead of the kinetic energy. Okay? Good? Okay. So let's do a different exercise. You've watched the video. Here's a different question for you. What happens if I do something like this? So I want you to consider that cart band collision. Okay, so you've seen it several times, and here's the question for you. I want you to draw different bar graphs representing the kinetic energy and the elastic potential energy. Now, of course, excuse me, I should put I'll put U spring here. So just match more of the notation that your book uses. So go ahead, take a minute or two, pause the video, and ask yourself, okay, well, if I'm drawing a bar chart representing the kinetic energy and the elastic potential energy, When the rubber band's unstretched, what would that look like? When it's halfway stretched, when it's fully stretched, and when it's a quarter stretched. Take a minute, go at that. I'll see you in a second. Okay, good. Well, hopefully you see, if we're dealing with the cart bands, everything's in the system. I want the cart band system, okay, and that's implicit because we're talking about potential energy at this point. So if I want, when it's completely unstretched, this means that no energy is stored in my rubber band. That means all of it, the total amount of energy, is kinetic. So I better do something like that. Okay. And fully stretched, should start there, keep going. Fully stretched means that the cart's no longer moving. All of my energy must now be stored as elastic potential energy. So unstretched, all the energy is kinetic. Fully stretched, all of the energy is potential. And now we have to figure out, what do the bar graphs for the kinetic energy and the elastic potential energy look like when it's halfway stretched or when it's a quarter stretched? And here's where I start trying to remember some of the rules. For example, energy G cannot disappear. That means, okay, well, if my work is, I have zero work, so it can't leave the system. Okay. That means that the sum, if I visually think about the two bars that I draw for the kinetic energy and the potential energy, if I think of stacking those two together, they have to equal a height of the total energy. So that's the first thing. If I stack those two bars together, they have to be the height of the total energy. Here's the next thing, and we can go even deeper here. We know that the potential energy, the spring potential energy, delta U spring, is given by 1/2 kx squared. Okay. So I'm looking here. If it's halfway stretched, that means it only has 1/4 of the potential energy. Quarter, I should say. If it's only halfway stretched, that means that I should draw something that's 1/4 the size of this big bar. Okay. So evidently, I'm going to do something like this. I'm just eyeballing it. That's about 1/4. And the kinetic energy still accounts for 3/4. Something like that. Okay. Now the last one, a quarter stretched. Well, a quarter squared is 1/16. Oh boy, that's even going to be harder. So a 16th, so I got to do 1/4 of that. So it's going to be something like, we'll do it like that and like this. Like that. Okay. Now you notice, okay, energy can't disappear. I stack those bars on top of each other. Yeah, that all works out. Okay. Looks good. Second of all, when it's a quarter stretched, I should have more kinetic energy when the rubber band is less stretched. And you notice that, of course, yes. Less energy when the rubber band is more stretched. Less kinetic energy when the rubber band is more stretched. So that works out great. So I think I'll leave it there for right now. I say, hey, thanks for your attention. I'll see you next time.